Hi, welcome back. In this lecture I want to talk about the read and write QPU instructions. Let's start with the read QPU instruction. The read operation is nothing else than a readout or a measurement process. In the textbooks and in the quantum computing papers, when we write the quantum circuit and we want to express a measurement, we often see these two symbols, this one and this one. So particularly this one really shows that the read operation is nothing else than a measurement. The read operation is somehow a unique QPU instruction in the sense that it returns random results according to a distribution of probabilities. So for instance, if we have a quantum system that with the two states both likely, the same probability to measure either state 0 or state 1, whenever we do a measurement, whenever we do a read operation, we have after the time we will roughly measure the state 0 and the other half of the time 1. So this is random process, so sometimes it's 1, sometimes 0. We might also have quite a long sequence of either 1 or 0, but if we have a large statistics, so if we have many measurements, we will see that the read operation will give the same amount of 0 and 1 state during the readout operation. So applying the read to a single qubit will return a value of either 0 or 1 with the probabilities that are determined by the square of the associated magnitude in the qubit state. So if we are using the circular notation in these two cases, you will see we have state 0 and state 1. They have the same probability after the measurement to measure either state 0 or state 1. You will see that roughly 50% of the times we will measure state 0 and 50% of the time we will measure state 1. In this case here at the bottom, you see that most of the time, so 85.4%, we will measure state 0. So the circle is filled with a larger part with respect to the state 1. So that means that the magnitude is also larger and also the probability. So the important point that we stressed in the previous lecture also that the relative phase of the qubits, so that is the phase of state 1 with respect to the phase of state 0, is the relative phase, does not really matter when we do a measurement. So you see here, for instance, there is a relative phase, but it doesn't really impact the measurement or the read operation in any way. An important point about quantum computing is about the reversible part. It turns out that the read and also write operation are irreversible operation. The reason for that we know that if we have a superposition of state of 0 and 1 state, we do operation, we get the state is 0 and 1, but we cannot go back to the original superposition. So in other words, any superposition of our quantum system or our multi-qubit system or one qubit system is actually irreversibly destroyed. So the read operation is the first example of irreversible QPU instruction in quantum computing. If we develop a quantum computing simulator or also we use one, we might think how to implement this read operation. So this is just a very simple Python function that emulate the read operation. You see that we have a variable here, possible outcomes. It's basically an array that whose length is equal to the number of states of our quantum system. So for one qubit, we will have two possible states. That means that we will have two possible outcomes. In the case of two qubits, we will have 4 possible quantum states. So these possible outcomes will be 4. When we calculate what is the magnitude, so we calculate the magnitude of the different state of our qubits, and we use this magnitude as the weights when we do the random sampling. So we have a random sampling over n possible outcomes, and then we use as the weights of the distribution, we use the magnitude of the state, and then we print here the results. One thing we can do in order to obtain a distribution of our measurement is actually to repeat this measurement many times. So you see in the simulator, often you have this n shot or n samples. There is actually the number of operation that the number of readout operation that we do during our read. So in this case, we have a Python function, we call it read multiple, and then we can provide an argument that is the number of shots, that is the number of measurement. And basically here what we do, we just have a loops that we iterate over, and then we make a measurements, and then we accumulate this measurement. And then we plot as a histogram what is the results of our n-shots measurement. So if we use this primitive quantum simulator, here we have we started from one state here, and then we add another gate, and then we obtain this circular notation, and then we applied the read multiple. So for instance, read multiple, it gives you this histogram. You see that roughly almost the same, right? Obviously there is a difference because these are a random operation. If we increase the number of shots, we will see that the difference will become smaller and smaller. In the case of simple read operation, if we do here, we just either measure sometime 1 and sometime 0. Let's talk about the write operation. The write operation allows us to initialize a QPU register before we operate on it. This is a deterministic process in the sense that it's the user deciding to initialize the system either in state 0 or 1, or if it's a multiple qubit, we can just pick it up one of the state. Using a read and a not, we can also construct a simple write. Remember that the read just gives us either 1 or 0. So the one particularity of the write QPU instruction that there is no write to superposition. So write operation does not allow us to prepare a qubit in arbitrary superposition with arbitrary magnitude and relative phase. And the reason for that the write is a classical operation, right? So as a user, we initialize the system, but because we are not in a quantum system, we cannot really initialize in a quantum superposition of state. So what we're going to do, we just initialize the system in a classical state is 0 and 1, and then we are going to operate with the gates, for instance, Hadamard gates, and like a rotation, in order to bring the system in quantum superposition. The write operation also a very simple operation for the quantum simulator. We just initialize a state with a certain probability that is, in this case, 100% probability. Right? So we pick up the state to initialize, and then we set it up, the probability to 100%. The read and write operation are not reversible because they destroy superposition, lose information, and we cannot go back and forth, right, from the results of the read and write operation. That means that once these operations are done, the analog values of the qubit, the magnitude, and the phase that characterize the superposition are gone forever. So this is the last slides, and talk to you soon.